Good afternoon, everyone. I'm Rob Capizzello, Executive Vice President of Services at Mariner, your host for the webinar. We know you're all very busy. Hope everybody's remaining safe, and we sincerely appreciate you joining us, taking some time out of your day. We're excited about the solutions you'll see today and hope this discussion will stimulate ideas as to how your organization may find value. I'll provide a little housekeeping info before I introduce and turn over the meeting to Mitch Landis from Connexus, Indiana, and today's speakers. You'll notice a Q&A box at the bottom of your screen. Please feel free to enter a question anytime, and at the conclusion of the presentation, we'll take time to get your questions answered. If time does not permit, we'll follow up with you after the webinar and or provide an opportunity for you to speak directly with our presenters about your particular challenge. So I'd like to now introduce Mitch Landis from Connexus, Indiana, who made it possible to bring this webinar to Indiana. Mitch is an engineer by training, has spent a career in technology development and deployment in both industry and academia. Currently, Mitch is the VP of Innovation and Digital Transformation for Connexus, Indiana, where his work focuses on ensuring that Indiana enhances its leadership position in advanced manufacturing and logistics through digital migration and digital adoption. Welcome, Mitch. I'll turn it over to you.
Thanks, Rob. Can you hear me?
Yes.
Yeah, okay. So first, let me echo the welcome and thank you for joining this afternoon. Thank you to Microsoft and Mariner who will be presenting, and thank you to Mesh Systems and Carmel, Indiana, another Microsoft Gold partner who brought this topic to our attention. And of course, thanks to the participants who are taking time out of their day to learn about this topic. I want to take just a couple minutes here to set the context. Most of you are familiar with Connexus, Indiana, and know that we're focused on accelerating, promoting, growing Indiana's advanced manufacturing and logistics sectors. We do that in a variety of ways. We connect businesses, educators, and government leaders through our councils and working groups. We motivate, prepare talent pipeline for advanced manufacturing and logistics. We share compelling stories about those who make things, move things in Indiana. And the part that I'm fortunate enough to lead anticipates impact of technology. Whether you want to call it Industry 4.0, Factory of the Future, Smart Manufacturing, or something else, it's clear that a digital transformation is underway. It's happening in all sectors, all regions of the global economy, particularly interesting in manufacturing where systems, processes are incredibly sophisticated, they're hardware and capital intensive often, much of which is legacy equipment in many cases, and it involves a blend of humans and machines. And so needed skill sets are evolving, plant capabilities and expectations are expanding, nature of work in many cases actually change. And so, and it's happening a bit unevenly because of cost and complexity, but a few leaders are out there in front making investments for the future, leveraging technology, and that actually poses some risk of a digital divide, not just in terms of employee skills, but also in terms of supply chains keeping up. So Connexus wants to make sure that to the fullest extent possible, the people, plants, operations that are so critical in our statewide economy are keeping an eye on the landscape of evolving technology to make measured, smart decisions to stay on the correct side of that potential divide. So, you know, we do a number of things, including emerging tech showcases like this. In this case, we highlight specific technology solutions, something that's early stage but commercially launched, something we think has potential and value proposition for advanced manufacturing and logistics, and something that fits within the suite of technologies that's commonly referred to as Industry 4.0. So Mariner fits well here with their mix of machine vision, IoT, AI techniques, and specific emphasis on quality inspections. Quality is pretty much top of the list when you ask AMLs what's most important to customers. And of course, Mariner's Gold partner status with Microsoft enables us to bring Microsoft into the discussion as an opening keynote here, so we can better understand some of the things they're doing to emphasize new solutions, manufacturing, supply chain, logistics. So with that said, I'd like to go ahead and introduce David Berea. who's the America's business leader for Microsoft's global manufacturing team. David is based in Detroit, Michigan, works with strategic customers to deliver business transformation programs enabled by advanced platforms, technologies, and industry solutions. So David, if you want to take us.
Great, thank you, Mitch. So hi, everyone. As Mitch said, I have the pleasure of working with a lot of industry leaders in manufacturing and really helping to deliver what we like to think of as next level business outcomes. I know in light of the current situation, transformation's a little bit of an afterthought. It's more around how to respond to this crisis, and then over time, how do you think about recovering? But I wanted to just kind of anchor the conversation in a couple of key themes. And I think that, you know, despite the timing and even scope of what a lot of companies are thinking about right now, there's still some key principles that apply, and I think will hopefully help to center your thinking around some of the things that we're going to deep dive on later in the discussion. So let me kind of open with this concept of a digital feedback loop. As you look at the way that most companies are trying to really think around this digital operating model, it's really anchored on being more customer focused, maybe having connected products, and being able to really enable employees. As we look at the core operating processes in most companies, you know, it's really a chance to bring all three of those things together. And so as we look at how we go to market and think about where companies really have the biggest opportunity for value creation, it's around getting connected to existing data. And I'm not sure who's controlling the slide, but if you can build this slide out, that would be great. So whether you're talking about a factory, whether you're talking about a distribution center, or even a value chain, we see really three levels of maturity in terms of these capabilities. Number one is really getting connected to the data. So this interplay between cloud technology and IoT platforms is really that first step. Being able to start to harvest the data for insights. In some cases, you can actually be opportunistic and start to apply some of these AI capabilities. and we'll give you some very specific examples of that in just a minute. But really over time, starting to move towards these closed feedback loops where you're either directing action or in some cases even making that autonomous. And so the concept of a digital twin is something that we'll unpack later, but think of it as a virtual model of the physical reality as it exists within supply chains, distribution centers, and plants. The problem that exists in most companies today is that legacy solutions and technology architectures don't really allow for rapid feedback or any type of response that's not directly enabled through humans. And so whether you're looking at a digital twin of a plant or an entire supply chain, it's really closing the loop between planning, execution, and then being able to report the results. Traditional ERP and MES systems don't have the ability to do that just by virtue of the way that they were designed. So if you can go to the next slide, I think as we look at manufacturing in particular, there's been a lot of programs that have come of age over the last couple of decades, right? Going all the way back to total quality management, some of the early principles around lean, value stream mapping, error proofing, and then even Six Sigma with process controls and trying to really start to move variation outside of the manufacturing process. Over the last few years, I think with rising top lines, we've seen a lot of companies kind of lose the expertise around operational excellence. A lot of these continuous improvement programs were driven by people using spreadsheets, right, and other paper-based tools. And so what's happened is that as the top line has grown, as there's been more products, as there's continued pressure to reduce the cycle time between concept to product launch, a lot of these sustainable results have actually dissipated. And so being able to not only do that at a single facility, but being able to scale it and then being able to use it as a way to unlock value and fund other innovations or other improvement programs has become a challenge. It's something we've heard directly from customers. If you can go ahead and build out the rest of the slide, please. What we see is really this concept of a next generation efficient frontier. And in fact, a lot of leading manufacturing companies have already delivered on this promise, whether you're talking about Industry 4.0 principles or alternative kind of digital models. This concept of being able to bring connectivity, flexible automation, and intelligence together is where we've seen just unbelievable step change improvements in traditional metrics, but also being able to move from islands of production to these integrated value networks is something that has been demonstrated through the World Economic Forum. They've talked about their original 16 lighthouse factories, and now I think there's 44. The early leaders are already looking at value chain integration as the next kind of wave of opportunity that they're pursuing. I think the other thing that I would highlight is that although this is a journey, most roadmaps take the shape of 3 distinct horizons, and think of that as capability maturity. Initially, it's around trying to take the data that exists, move it into a cloud type of a data model, and then being able to identify where there's blind spots or holes in the workflow. And that second horizon is starting to move from reactive data that's inherent in traditional transaction systems to becoming more real-time, and then opportunistically starting to use prediction as a way to get in front of events and other unplanned activities that may be impairing performance. And then finally move into this concept of really bringing everything together into a next generation digital operating model. And that's going to look different for each company, but I think there's a lot of lessons and a lot of things that have been learned that can help companies embarking on this journey move a lot faster. So if you can go to the next slide, please. I think as we look at how to apply artificial intelligence, specifically in manufacturing, we see too many companies leading with technology. This tends to be a use case driven conversation. It's kind of focused on doing a proof of concept. In too many companies, I think the latest stats I've seen is 2 out of 3 usually fail, either because they haven't defined success criteria up front, or they haven't created a business case that allows them to scale once they've proven that the technology works. And so as we look at AI, and you see this dark bar at the bottom, we really like to unpack it into the enabling capabilities. AI is more of an umbrella. As you look at the things around object recognition, speech recognition, many would argue that that's not even innovative, right? Those are things that have already been indoctrinated into the way that we live our lives every day. Some of the other things around deep learning and even machine learning are still evolving in the manufacturing environment. So rather than starting from the bottoms up, we like to go back to what manufacturing is held accountable for. And it's really the 4 things along the top. It's optimizing operations, typically measured by either cost or throughput. Productivity can be an enterprise type focus, or even down to an operator or a piece of equipment level focus. A lot of this is focused on continuing to stay relevant and growth through new products and new markets, and then being able to make sure that what gets delivered is delivering a good experience and customers are going to come back. So being able to kind of connect those two, in the middle are a lot of the different scenarios where we have been able to either deliver AI on our own or through partners like Mariner. And so in this case, we want to really double click on the cognitive quality area, along with some of the smart manufacturing capabilities that Mariner brings through Spyglass and some of their other solutions. So hopefully this has been helpful to just kind of lay some groundwork and context for what we want to share with you going forward. I think in future sessions, we'll be looking to your feedback in terms of other areas that would be of interest and where we can bring some insight and some real world examples of how this technology is driving business outcomes today. So with that, I will pass it off to Robbie and we'll kind of get into the rest of the agenda.
Thank you, David. Just wanted to remind everyone there's a Q&A button at the bottom of the screen. So if you have questions, please input them through that button. My name is Robbie Jones. I'm the Enterprise Sales Manager at Mariner. I've been working in manufacturing for about 19 years now, and really over the last 5 years, really focused on data and technology on the factory floor. And we believe David was touching on it, the tools available from Microsoft today really do a great job of enabling manufacturers to take advantage of all the data they produce. So that's what we want to talk about here. Specifically, I'll start diving into a little bit about Mariner and who we are. We're a analytics services company, a 22-year-old company. We've been a Microsoft partner our whole time in existence. And what we really started seeing about 5 to 6 years ago was some repeatable patterns in the work we were doing for manufacturers. And when we recognized those events repeating, we started developing point solutions. And I'm specifically going to be speaking about our Spyglass connected factory solution. After me, Stephen will join and talk a little bit about Spyglass visual inspection. So we still maintain our skills and our staff to handle traditional analytics applications, but specifically using the tools from Microsoft, we want to dive into Spyglass connected factory and how can that help you in the manufacturing environment today. So what is Spyglass connected factory? We're viewing it as your virtual production manager. And in order to implement this solution, you have to be a change agent. Considering today's times, change is not that hard. Everyone's experiencing it on a massive scale right now. So how can we use that to our benefit? Typically, we're trying to guide you and help you with this change. Mitch mentioned there's a lot of terms around it today. Digital transformation, industry 4.0, lots of different ways to describe it, but really we want to start capitalizing on your data and letting that point you in the right direction to improve your manufacturing process. So what are some of the problems with the current manufacturing processes? The Toyota production system, really developed from 1948 to 1975, has been the backbone of manufacturing for the last 45 years. Operational excellence, continuous improvement, lean manufacturing, a lot of different terms that are all similar. And manufacturers today are really good at what they do. There's a lot of expertise, a lot of tribal knowledge. Maintenance teams are excellent at responding to outages and fixing problems, getting production back up and running quickly. So over 45 years, these companies like yourselves have been squeezing as much water out of those rocks as possible. If you've optimized your solutions as far as you can with today's technology, what more can you do? We believe this is where the data can expose you to a whole new tool set that can be utilized to gain additional value, improve production, improve throughput, yield, quality, reduce waste, and target those traditional lean areas with better focused Kaizens. So being a virtual production manager, in the first place, none of this is possible until you have a centralized place to bring in all of your disparate data together, to have a single repository that you can view across your empire. This also allows you to start experimenting with AI and running some artificial intelligence projects. The alerting and monitoring piece. really in manufacturing, it's about knowing something sooner. So if we're bringing all the pertinent data together, we can inform your employees quicker than ever before with this new technology. These continuous improvement teams can derive tremendous benefit from this in ways they've never been able to explore before. You know, when we can notify you of emergent conditions that are going to adversely affect your quality or increase waste, you can react quicker and point you to the right direction so you can take action. OEE analytics. Some of you may be familiar with overall equipment effectiveness. You've got to benchmark where you're at today in order to determine how you can improve. David touched on some of the issues with the production and your abilities to continuously improve. This is a tool that comes standard with Spyglass and can help you identify where your lowest hanging fruit is, what you need to investigate. And then ultimately predictive maintenance. Can we have machines and processes raise their hand when there's a potential problem about to occur? So I mentioned the maintenance teams that are excellent today. They're even the best reactive teams. Wouldn't they be better if they could analyze, hey, we need to take care of this Friday before we have an unplanned downtime event this weekend? Or no, it looks like we're going to be able to limp through the weekend, so let's leave it and we'll address it on Monday when we come back. So now I want to shift gears a little bit and share some specific use cases. This first one is from Milliken, and they're a global chemical and textile company based out of South Carolina. When they first came to us, they had some specific business challenges. They didn't have any idea how their valves and motors were performing. They couldn't do any detailed root cause analysis. And the main reason they came to us was the engineers were spending excessive hours just blending data. In fact, the engineer joked that it was a running joke internally that they were extremely high paid to just merge data sets together. So that was really how we started with them, is trying to provide some better visibility into what they should be doing to improve their manufacturing process. So let's move on to the results that we were able to deliver. And one of the benefits here was giving them a list of equipment that could be pulled up, current forecasted maintenance that was set and planned, and in the event of an unplanned outage, they could pull in, take care of, and really kind of recoup some of that lost time. You can see here, according to the chart, the maintenance was set for 6,000 hours and nothing's even at halfway, even though the date's showing it's due in May. Maybe the machines haven't been running. They've been shut down due to coronavirus. So clearly they're not going to pull anything up in this instance, but here you have hard data to show you the current status and just to allow you to make better informed decisions. The AI use cases, once we had a majority of their data all centralized, they were able to take on an AI project, and it was specifically around some of their compressors unexpectedly shutting down. And in manufacturing, when all your compressors shut down, you can imagine the problems that caused on your shop floor. They brought in the OEMs, and it was random. Nobody could figure it out, even their expert maintenance team. So by analyzing all the data, we were able to, what we like to call, finding a pony. And through all that noise, the AI was able to look at all that telemetry and recognize there was a problem with a specific piece of equipment. Once we highlighted that, the engineers knew exactly what the problem was. They bought a new one, replaced it, solved the problem. Now, this is an AI case that is not ongoing, but it was a tool, a new tool for them that could be used to solve a problem. And it's a win for them. And then blending data. The engineer got 7 different sources and manually blended those together every week just to know where they needed to go and what they needed to focus on. And one of the benefits here of Spyglass Connected Factory is taking the mundane tasks like that and serving that up, making it self-serve. You know, it's at the engineer's fingertips, on their phone, on their tablet, on their desktop, and they don't have to do anything to it. They were specific about how they wanted to see the data, so we shaped that and delivers that to them on a regular basis now, eliminating that mundane task. So another equipment manufacturer wanted to collect telemetry to do better traceability and to really target their Kaizen approach. Trying to balance first shift, second shift, third shift, and optimize their production patterns. The result was they're able to increase their overall throughput, quality on everything they make. Does this raw material run better on machine X or machine Y? And using the data to help them forecast what should be run where and why. You know, any good engineer is going to want to ask why and be able to investigate it. And we can get granular enough with all the data to really prove it throughout the organization. Another example is, this was actually a safety project where certain actions, part of the standard operating procedures, need to happen on a regular basis. And to avoid operators pencil whipping it, you know, at the beginning of their shift, just filling in all the information, yep, I checked it, or at the very end of their shift, just saying, yep, everything's where it should be, we're able to monitor this real time. And what I really liked about this solution is there was a specific safety action that needed to happen every 24 hours. If that did not happen, there was an alert sent to the manager. After 15 minutes, if the manager did not respond, there was an alert sent to their manager. So that escalation rule is built into this solution. So it's going to go as high as it needs to go till someone will finally take care of this emergent safety condition. The next application is from Automotive. I think they're a tier 2 supplier here. And you'll hear a little more about this from Stephen. If you go back, there we go. This is making fabric for headliners and seats. And the first bullet you see there was around the fabric flowing in the line. They wanted to monitor some traditional telemetry, because exceeding upper or lower limits of any of these variables can result in bad quality product. So the sooner they can know about this, you know, SPC out of control alerts, they can react. They can stop the line, they can make adjustments, and instead of wasting complete rolls of fabric, they can have a 100-yard section they have to cut out. So tremendous amount of savings associated with these alerts. Additionally, in the same application, we're also able to look for repeatable defects. You know, if we see a trend of dye stains occurring 4 in a row, 5 in a row, 6 in a row, we can set the rule to whatever set point the customer wants and alert the right people. You know, dye stains need to go to the dye department. Do we have new raw materials from a different supplier that's changed up? Do we have a problem with the dye staining machine? Is the tip worn? Has it been bent? You know, are we getting inadequate dye? Lots of different variables that we can look for and put into place. But the beauty is it quickly notifies us of the real root cause and can point us to the right area to solve the problem. All right, a couple more on where Spyglass and AI kind of merge. And this one touches on the mean cycle time between failure. Kind of tied into predictive maintenance. And the nice piece here is you don't always run the same exact thing on the same exact line every day. There may be some products that are more difficult to run and some that are easier. So we can take this into account and recognize, you know, we're running easy today and for the next 2 weeks. So instead of servicing the machines at 6,000 hours, we can push it to 8,000. Or we're going to be running the most difficult products through our line today, the biggest, the heaviest, the thickest, and our pumps are going to have to work extra hard to push the peanut butter through. So maybe we're going to need a 4,000 hour service. But personalizing your mean cycle time between failure is an excellent AI application to improve your overall process. Another, I mentioned earlier, OEE. When it comes to OEE, there's a lot of variables that come into play. Where do you start? You know, what's the one thing you can change that's going to have the biggest positive impact for you? Sometimes you can look at 6 to 7 things with the human eye and make a connection. But if you're talking about hundreds or thousands of variables, no human's going to be able to see that. Humans want to look for the outliers, the crazy events, because those are easy to spot and you can start solving them. But the mundane, that's where we come into play, and you can allow the computer tools, these software tools, this artificial intelligence to do all the heavy lifting, so you don't have egos that are exhausted, ego or exhaustion associated with humans. So some of the questions we start out with when we're engaging with the company to help them get started is, what would you like to know from your data? If we could serve it up in a different manner, would you be able to take action? What's your number 1 cause of downtime? You know, a lot of you may know that, but what's your number 3, 4, 5? How do you know? Do you have proof? Can we believe your proof? Are there things in your current process that would probably be ponies, but you can't see it because there's so much noise in the data? You know, you can see 6 or 7, as I mentioned, but what about 150 variables blended together? And then ultimately, would you like to better understand how your process works? If we can create some visualizations that show you that through the collection of all your data into a single repository, would that be valuable? What's the business value here for your teams? And tying into the business value, the way we approach it is defining success. David mentioned this as well. We want to really determine where's the business value, and that's our first step. And then we install trained Spyglass connected factory on your lines to recognize the emergent events. And then we're helping you become the change agent to promote this throughout your organization and use it to help others buy into this new technology and recognize that this has tremendous benefits on the concrete for your organization. We approach this, we put a lot of emphasis on defining success. We actually have a money back guarantee. So if we can't meet the success criteria we determined at the beginning of the project, you do not pay for this project at all. So for more information, you can obviously visit our website and email me directly at robbie.jones@mariner-usa.com. And with that, I'll turn it over to Professor Stephen Welch, and he is going to walk us through our Spyglass visual inspection solution. Thank you.
Great, thank you, Robbie. Hopefully you guys can hear me okay. Thanks to David and Mitch for those for the introduction and some Microsoft context. Let me go ahead and hop to my slide here. And thank you to our audience for joining us today. I'm sure that you're busy, and thanks for taking the time to join us today. Hopefully this time is worthwhile. I think that we hopefully set up some cool explanations of some of the work that we're doing. And during my time here, I'll dive into some applications of deep learning that we're deploying at Mariner, specifically for quality inspection. So I'll go ahead and hop right into it. And this is part of a product that we sell called Spyglass Visual Inspection. And I'd like to kind of start with a real application here, or with some real data. It's going to be helpful to kind of give you an idea of the kind of data that we'd be really looking at in a project. So imagine with me for a second that you woke up tomorrow morning and you were in charge of quality for a fabric manufacturer. And let's see how to decide which pieces of fabric or which images represented good fabric that you could ship to a customer, right? So which of those 4, just take a second to think which 4 of those, of those 4 are good and which ones are bad. So while you're thinking about that, let me give you a little bit of context about where this data came from. So this is from one of our customers. This is real data from a real production line. So they use a machine vision system. So machine vision has been around in manufacturing for 30 or 40 years at this point. And generally, machine vision technology has gotten very good at the hardware components. So this is a fabric system designed just for fabric. The fabric flies through the bottom of this machine at about 85 yards a minute. And there's 8 cameras up here. And these cameras are taking pictures of the fabric as it flies by. These are some example pictures from the roll. And the output of this system is what's called a defect map, and that's this scatter plot down here. So every point on this scatter plot is a location where the current system believes there to be a defect. And this map is really important because in the next stages of production, like Robbie mentioned, this map is actually used to decide which parts of fabric to cut out so they don't send defective fabric to the customer. The challenge, and this is typical of many machine vision systems today, is this system for this customer struggled with a high false positive or false reject rate. So what that means is that in practice, up to about 40% of these points would actually not be defects. And that sounds really high, but it's actually really common. There's some very difficult computer vision challenges that occur regardless of how good your imaging capabilities are. And we'll talk about those in some more detail. But this is the problem that the customer was up against. So they had great hardware, a great vision system, but they still had to do a significant amount of manual human visual inspection, which is subject to all kinds of problems. Because they weren't able to reliably tease apart the true defects from the non-defects. So why do traditional vision systems struggle? So here's kind of an overview, and I'm also a computer vision professor as an adjunct in my spare time, so I can talk your ear off about this. So if you have any questions, please ask. But here's traditionally how computer vision has worked for manufacturing applications and for many applications out there. So traditionally, there's going to be some kind of image capture component, and that really hasn't changed. There's going to be some kind of compute component running some kind of software, and the heart of that software is a computer vision algorithm, right? And its job is to decide if an image is defective or not, or what kind of defects it has, or perform some kind of measurement or metrology on these images. It's designed to get some kind of information out of these images. At the end of the day, images are just data. They're just pixel values, right? So typically, in the past, this process has been broken into two parts. So the first part is called feature extraction. And in feature extraction, what we do is we take some kind of piece of math, a little mathematical operator, and we try to extract measures or metrics that are going to help us make an overall decision. So in this example here, I'm showing the contrast. So this is a pretty common feature to use in computer vision. So I'm taking a little sliding window, I'm moving it over the image, and for every little sliding window region, I'm measuring the difference between the darkest and the brightest pixel. These regions are glowing because they have a very high difference between dark and light regions. And as you can imagine, high contrast could mean a defect, maybe, right? Of course, contrast alone is not enough to make a decision, so typically features like contrast are combined with other features. For example, you might measure the defect size. So you might have some way to measure the defect size, and maybe you can combine those two features together to make a decision. So those features, and typically many more features, are then passed into a decisioning step. Sometimes this decisioning step is learned using a technique called machine learning, but often this is actually done manually. So often your quality engineers on your floor will actually be in charge, or you might have someone running the vision system who needs to tune these thresholds to make these recipes to make the best overall decision. So this is traditionally how machine vision has worked, and in many applications this is fine, but there are areas, and increasingly more and more areas as capabilities increase, where this technique kind of falls apart. So what we do at Spyglass, actually, before I hop into that, let me go back to the question I asked. Yeah, cool. So pause on that for 1 second. This is traditionally how machine vision has worked. So let me answer the question here. So which of these show defects? And I'll go ahead and put the answer up. So to a trained quality expert at the customer we work with on this project, this is easy. So they can tell you this immediately. It took me a little while to learn, but if you look carefully, so this is good fabric. We can ship this, no problem. This fabric has a hole in it. It's defective, don't ship it. The real challenge is examples like this. So this is actually what's called flock. This is a piece of material that happens to be just on the fabric. It can be brushed away. It's not a defect. This is a stain. This is an oil stain, so this is not going anywhere. As you can imagine, using the techniques that we just talked about, using feature extraction followed by decisioning, it can be very hard to write a computer vision algorithm that can tell this apart from this. So they have similar contrast, right? They have similar sizes. So you really have to get into some high order complex features to make distinctions like this. And 10 years ago, this really was not an impossible problem, but a very, very difficult computer vision problem to solve. So the big change since then, and I'll get into a little more detail here, but the big change is that computer vision has really been dramatically upended in the last 5 to 10 years by a technique called deep learning. And at Spyglass, really at Spyglass Visual Inspection, our main value proposition is deploying and maintaining and training deep learning models into manufacturing environments. So really at a high level, you can think of us as replacing that traditional two-step computer vision process with the deep learning process. Now, there are some trade-offs you make when doing deep learning. You have to do some work to set things up, and there are certainly many advantages to the old approach, but there's one big advantage to deep learning that I want to talk about here, and it's really performance. So let me hop into a graph here. Yep, great. So if you're thinking about, why deep learning, and deep learning is certainly not right for every application. Just like Robbie said, you first need, well, I shouldn't say a lot of data, but you need good quality data to get started. And there's other reasons why you may or may not choose to use deep learning. And hopefully this talk gives you a better sense for where deep learning is appropriate and where it's really getting traction in manufacturing. But the main compelling use case for deep learning really is performance. So this shows performance over time on what is probably the hardest benchmark, or it was the hardest benchmark in computer vision. So this is an open source data set called ImageNet. It has around 20 million images in it, but around 1 million of them are used for this classification challenge. So every year, researchers submit their algorithms. And the challenge is this. So given roughly 1 million labeled images, the images have labels that span around 1,000 different classes. So things like dogs, cats, sailboats, chickens, all that kind of different typical classes you'd see in images. So the idea is you train a model off around 900,000 of those images, and then you test it on around 100,000 that are in a holdout set. And back in 2010, the very best models in the world had an error rate of around 28%. This is not that long ago, right? 10 years ago. And the very best model in the world got it wrong 28% of the time. And that's actually given 5 guesses. In 2012, though, something really important happened. So this group at the University of Toronto, led by Jeff Hinton, they published a paper called AlexNet. And in that paper, on this data set, they increased performance by about 40%. This was a big jump. This is when people started kind of talking about deep learning. So they did that by deploying a single unified deep learning model, just like we've been talking about. So instead of using a 2-step process of feature extraction followed by decisioning, they used a unified deep learning model. And by doing that, again, they were able to increase performance by about 40%. And then in subsequent years, researchers, by largely improving on the same technology, were able to, for the first time in 2015, beat human performance on this ImageNet dataset. This is remarkable. This is huge progress in 4 or 5 years. This ResNet technology, this came out of some Microsoft research. It's open source, public domain now, but it came out of some Microsoft research. And this is actually what we deploy in our system. So all the results you'll see today are from ResNet deep learning model architecture. So that's a little bit about why deep learning. But let's tie it back to the business case, right? What did this do for this customer? So for this customer, we created a labeled data set. We trained a model like we normally do. We deployed it into production. It's in full production now. And here's what it can do, right? So given the right application, these are some of the results you can achieve with deep learning. So this is the defect map before, right? These are all the points where there's defects or supposed defects. All the blue dots are actually false positives, and with about 98% accuracy, our model removes those and correctly classifies the remaining defects. So if you think about it, if in the next stages of production, when they go to actually cut out the fabric that has defects, their process is dramatically changed, right? This map is significantly cleaner, and they can begin to automate these processes. Just for some numbers for you, so the accuracy, maybe that sounds good, maybe it doesn't. Accuracy usually is not directly tied to business value, but if we look at 2 other metrics for this customer, we can really see a bit more of the story about the value that this is providing. So I mentioned that their false positive rate was on the order of 30 to 40% before. So we were able to drop that to around 1.3, and it's actually lower now. But this is a 30x reduction in false positives or false rejects. So this is not, deep learning is not making a 30% improvement, it's making a 30 times improvement, right? So that's crazy, right? There's definitely some hype around deep learning, but when you find the right application, it really can deliver some just tremendous results. And that's why you're seeing excitement around it. And then finally, excuse me, we also compared this to manual inspection. So on average, we do about 2 to 5 times better than manual inspection. And there's kind of an interesting maybe catch-22 here. So if you remember the process, so to train these models, we start with a labeled data set, right? So a question you might ask is, okay, if a human expert labeled this data and we trained a model from the data, how is the model then beating humans, right? So the answer is that when they do manual inspection, and for most manufacturers, it can be a real challenge to have your inspectors kind of be on their A game all day, and it's hard to get resources to do that. So humans really aren't great at just watching products go by, right? That's not a task that humans are well suited to. And later in the talk, we'll talk a little bit about upskilling and how we really think that that AI is enabling some of these workers who would have looked at a line before to do data labeling, and to actually, with doing data labeling, they can actually be dramatically more efficient because we can scale these workers' abilities dramatically with AI, where they're not looking at every product, they're looking at, let's say, 1% of the products that need to be labeled. And we can really use human efforts in a more intelligent way. So that's the kind of results that we're seeing. And this is what we'd say this is a really nice use case because it really drives some really great business value. And this is an area where we think deep learning is just a really terrific fit. So that's a use case. Hopefully that all makes sense. I want to kind of expand a little bit here with the time that we have remaining. And I want to talk a little bit more about deep learning in general. So hopefully that example gives you a feeling for where deep learning does well. And now, like I said, I'd like to get into a little bit more context. So if we kind of zoom out and think about the whole industry, so this is a really great survey from Vision System Design magazine. This was conducted late last year. And this kind of gives us an idea of the penetration of deep learning by various industries. So I've just laid out, hopefully in some convincing detail, that in the right application, deep learning can really deliver a ton of value, right? But we're still only seeing penetrations of 20 to 30% across various industries. So at Mariner, we're curious why, right? Why is this not proliferating more, right? Is it just moving slowly? Are there certain barriers to adoption? So we think there's really 6 big reasons why we don't see widespread deep learning yet. And we think that walking through these reasons hopefully gives you more context for where deep learning is a good fit and where it's not, and hopefully informs your thinking about where and how to apply deep learning into manufacturing applications. So we divided these into 2 columns here, right? So one is myths around deep learning, and then one is the challenges around deep learning. So there's a few things that we've noticed by talking to a lot of customers that really slow down deep learning adoption that just aren't true. And those are these 3 myths. So let's take these one at a time, and we'll actually show you some real examples to address and kind of talk about these myths. The first myth is that deep learning models need to be trained on very large data sets. So instead of me just telling you that that's wrong, let me show you a real example. And I think this will give you more of a feel for really how this technology works. It's really remarkable technology. It's a cool time to be working in this field. So let me show you an example with a real data set. So this is called the MVTech data set. This is from a computer vision company, or a computer vision for manufacturing company called MVTech. They have open sourced this data set, which is something we need more of in manufacturing. Manufacturers generally do not share a lot of data, so we're very excited to have a data set like this available. So each column here represents a different type of product category, and I'm showing some samples from that set of images. And the number here, that's the number of images, right? So they have 434 examples of pills, 370 examples of cables. This gives you kind of an idea for the scale of the data set. So think, 200 to 500 examples of each category. And we'll take just one category and we'll walk through some numbers here and kind of give you a feel for how training these models works. So we'll take the leather category first. And generally, when we start one of these engagements with our customers, first we need to figure out what type of deep learning model is going to be appropriate. So there's many ways to apply deep learning for computer vision. The simplest way is to do what's called classification. So classification is pretty simple. It's how we solve the fabric problem we just showed you. The idea is that you hand us an image and we hand you a classification. So if you hand us this image, hopefully we'll say that is a fold defect. It's the simplest, and it doesn't tell you, where the defect is. It just says somewhere in this image, I see this kind of defect. Classification might sound a little simple, but it is easier to label and easier to train. So generally, we recommend classification as a good starting point. Now, for some manufacturers, they have more complex problems and they need a more expressive model. And the next kind of level up here is to do detection. So in detection, the job of the machine learning model is to do 2 things. So one, tell you what's in the image. So say, hey, I see a poke right here. but also to tell you where it is. So a detection model will give you a bounding box, so they'll give you the coordinates of a bounding box. So you know the size of the defect, where it is, and what it is, right? That's kind of the next level. And then finally, segmentation. And there's more methods than this, but these are kind of the most common. In segmentation, we take it a step further and we say, okay, I'm going to tell you what's in the image, and I'm going to tell you down to the pixel level where that defect is. So we're going to say, hey, this fold corresponds to these pixels, right? This MVTech dataset is great because it has labels for all of these. We're going to show classification here, but the results that we'll share will really generalize to different deep learning approaches. But this is generally where we start with customers, is by talking about what kind of deep learning approach is going to be appropriate. So to show you the kind of scale and the kind of what this looks like generally with most of our deployments and customers, let me walk through actually training a model. So I mentioned that we use this ResNet deep learning model. So we'll actually train a ResNet model here. We split our data into testing and training. And we're going to show you two techniques here. So we're talking about this misconception that you need a huge amount of data to train a deep learning model. And that's really, as I said, not true. It was at the beginning. So I mentioned that the first successful deep learning models, AlexNet being one of them, were trained on around 1 million images. So it turns out what you can do, this is really cool, it's called transfer learning. So what you do, you train a model once on a big data set, like that ImageNet data set, and then you fine tune it or you refine it on, like, let's say, a customer data set, for example. So on the next page here, we'll show you two different modeling results. One from training from scratch, so just starting with a totally randomly initialized model, which is how you normally train these things. And then we'll show you transfer learning, where we take a model that was trained off dogs and cats in this big open source data set, and then we fine tune it on the leather data set. And just to give you a sense for the scale of data here, right, we have for our defect classes, we have on the order of 10 to 20 defect classes, so not a very large number, right? So we're not training on a giant data set, right? This is, you could collect a data set like this in many applications within a day or two. So we're not talking about a huge scale here. Okay, so here are the results, and I'm showing these in a confusion matrix, which hopefully isn't confusing. They're not too bad, I promise. So this is showing you how the model got confused. So this is the model that was trained from scratch. It didn't do great. It's got 78% accuracy, better than guessing, but not amazing. And what this confusion matrix is showing you, it's showing you where the model got it wrong. So for example, this 5 means that there were 5 images in the training set or the testing set. There were 5 images where the label from the human is color, it's a color defect, but the model says it's good, right? So this is a certain kind of confusion. And as you can imagine, different types of getting confused are worse than others, right? So if I say that a bunch of defective products are good, that's different than saying a bunch of good products are defective, right? So generally early on, we'll talk through customers through what's called their precision and recall rates, which helps them better quantify and understand exactly the nuance of how the model's doing. So this is the model trained from scratch. This is the model trained using transfer learning. So this took about 10 minutes to train on my GPU desktop computer using our Spyglass modeling software. And it achieves 100% accuracy in 10 minutes. So this is remarkable. So 10 years ago, this just was not possible. You could not, this is a hard problem, right? If you look at the detail of some of the distinctions we're trying to make, like look at a cut versus a poke, if you tried to solve this with traditional computer vision, it was probably doable, but difficult. And now we can do it, you know, as Robbie mentioned, I teach a computer vision class at the University of North Carolina. It's a graduate level class. Most of my students by the end of the class could train one of these models in, you know, half an hour. And the fact that that is achievable is just remarkable. So the technology has just come a huge way in 5 years. I'll show you one more example, actually 2 more quick examples, then we'll move on. But just to show you another one. So this is carpet, a different defect category or a different product category. We have different kinds of defects here, like holes and color defects. The metal one is really interesting. You have to look really closely. There's actually little pieces of metal on the carpet that blend in really, really well. This would also be a big challenge for traditional computer vision, right? Because look how close the colors are, right? That's really, really challenging. So again, training ResNet, we're able to get about 99% accuracy in about 15 minutes. We get one wrong on our validation set. It's this one. We mistake a thread defect for a hole defect. Generally in production, if you mistake 2 different kinds of defects, that's much less costly in terms of return on investment than mistaking a good for a defective product. So this is certainly a result we'll share and put on a dashboard for our customers, but it's not something that we are too worried about usually. And then finally, I wouldn't want to leave you with the impression that deep learning is a magical box that always gets the answer right, because it certainly is not. There's lots of nuance and detail to how you train these things, and we'll get into that in the second section here. But I just wanted to show you an example where deep learning does not do great. So I picked a harder category. These are screws. And look at the nature of the defects here, right? So manipulated front. So if you look carefully, the tip of the screw has been bent or pushed in, right? That's a pretty subtle thing to see. We can see it as humans, but it's pretty subtle defect. Scratched head has a little imperfection here. And this is an example, as you can probably tell, that we're not going to do great at. There are ways to do well at problems like this, but let me go ahead and hop into the results here. So we get about 74% accuracy. So again, better than guessing, but not great. And the kind of the story here is that we don't have a ton of data. You know, we don't have to have huge amounts of data. We're talking about 20 to 30 examples. And for a harder problem like this, for a customer, we would generally recommend collecting more data or consider using a detection-based approach. Because if you used a detection algorithm, you would be actually kind of focusing the algorithm's attention on the defect areas, and that may achieve better performance here. So just to kind of show you a negative example where, you know, it's not a completely magical black box, right? So, and again, part of the reason here is these are more subtle defects. And fortunately, you can train these models pretty quickly and see, you know, what's going to work and what's not. Okay, so hopefully that makes sense. So you do not need a huge data set to deploy this technology. That's not a barrier. So if that's stopping you, don't let it. The next one is that deep learning models take a long time to train. You might have heard stories out of Google or places about models taking weeks to train, which can be true. Excuse me. And some models today still take a long time to train, depending on the data sets and the architecture. But let me just give you a real life production example from our system. So this is a customer that we have been in production on for a while, long enough that we've done a number of training and labeling exercises with them. And we do a labeling call every week to continue monitoring model health and building our label data set. And with this customer, we have around 35,000 labeled examples. So we have a nice big data set. And this is really nice because it allows you to explore different questions like how long will it take to train my model versus how much data do I have? Or questions like how does performance improve with the size of my data set? So I just want to call out this graph on the left here. So here what we're doing is we're taking a random sample of our data set and we're slowly adding more and more data and we're seeing how long does it take our model to converge, right? And this is production grade deep learning. This is not a science experiment by any means. This is a large data set from a customer. And as you look carefully here around a data set of, let's say, 4,000 to 5,000, it's taking between 20 and 30 minutes to train a model. And it scales quite linearly, and by the time we get to 30,000 examples, we're looking at about an hour. So this is not, it's not weeks to train. I'd say worst case, we're looking at a matter of hours. And you can also accelerate these things by using more powerful compute. This is a single GPU training. So really, the training time can be a challenge, but there's lots of ways around that. And then finally, one thing that used to be true that we still kind of hear, that we hear from time to time, is that you need a data scientist or a machine learning expert on staff to use deep learning. That did used to be true, probably 6 years ago. Today, that's just not the case. So there's a number of really great tools on the market. I'll give a quick plug to ours, Spyglass Visual Inspection, but there's other tools out there as well. And these allow you to train these models without writing any code. And that's a big deal, right? And we're seeing this shift where it used to, knowing about neural networks and programming in Python and TensorFlow, that used to really matter. But now what really is starting to matter is actually the subject matter expert. So the thing that we need the most are more experts who know about fabric quality, right? The customer's experts. They really provide the value because they're making that labeled data set, and the model is really a reflection of that. So we think this is really shifting, and we're excited for that shift in the industry where really we think that this technology can really empower domain experts who aren't neural network experts. So I'm going to take a quick sip of water, and we'll talk about deep learning challenges. Okay, great. So those are a few myths. And now we knocked these out, I think. Hopefully we've made a pretty good argument that these are not things to be concerned about. But at the same time, there really are real challenges. There are real things that make doing this difficult in practice. So for us, we've seen around 3 areas that make it tough to get these things deployed. And we actually spend most of our time here. Most of the time we spend on product development and our service engagements are spent solving usually one of these three problems. So I have kind of a detailed breakdown for you here of why each of these areas is hard. And first, let's talk a little bit about deployment, right? Why is deployment hard? And honestly, deployment is significantly harder than training. Like I said, getting the results I've shown you thus far, really most of the students in my class can do it. It's not too difficult. The tools are getting really, really good. Deployment is harder though. One reason is that you have to have a high-powered computer, usually in the factory, to be able to keep up with the processing you have to do. Another challenge is that many manufacturers have made investments in hardware. Often there's significant vision systems in place already, so you may have to integrate with those. And then third, as far as integration is concerned, there aren't a lot of open standards for vision. So there's good standards for PLCs, for example, but as far as getting images off systems, there really is all kinds of integration challenges. So when we set out to create Spyglass Visual Inspection about a year and a half ago, we really took these challenges to heart and leveraging our relationship with Microsoft, really worked to build what we think is the right stack to get these deep learning models deployed, productionalized, and reliable into manufacturing environments. So this is where we landed. So you can see kind of our inputs and outputs here. So we're interfacing with existing vision systems typically. We will work with customers who do not have vision systems, but we generally bring in a systems integrator to build out the hardware. And our system, Spyglass, takes in images either over the network or through protocols like GIGI, for example. Our system lives in two places. So one is on the factory floor. So we deploy Linux-based GPU machines on the factory floor. And we have a cloud component as well. And these two work together, we think, in a really powerful way. So a lot of times when manufacturers hear cloud, they have some aversions, which is totally fair. We get it. So we've built our system in a really careful way in that if your internet goes down, even for, let's say, a week, we can still be in production. We're still going to process images. We're still going to make predictions. No problem. We use the cloud for the things that we think it's most useful for. So we use it for long-term storage, for collecting your data, retraining models, for quality analytics, for dashboards, for monitoring and alerting. All these things that are important, but we do not use the cloud to make that factory floor decision. So the decisions from our systems are generally fed back into your production line, usually through TCP/IP over Ethernet or through analog control signals. So that really is our deployment stack. And as you can imagine, there's significant engineering work that goes into this. You know, as we've said, we're Microsoft partners, so we are leveraging the Microsoft ecosystem, but there's still, you know, a significant amount of engineering effort that goes into making these systems reliable and scalable. So that's really where we spend a lot of our time working on this deployment challenge in deep learning. And I'd say that that is a key area of focus for us. The second area where we see challenges is in model maintenance. So this is, I think, a really interesting area that you're not hearing too many folks in manufacturing talk about quite yet. So in other industries, so before I was in manufacturing, I worked in autonomous driving. In autonomous driving, you kind of have to use deep learning, right? So, you know, you're not going to get away with traditional machine vision for most of the problems you have to solve. So deep learning penetration is probably 90% or something. And in other industries as well, like financial, Google, for example, in search uses deep learning algorithms. And in these industries, they're kind of a little bit ahead of manufacturing in some ways, I would say, and they've figured out the tooling and the infrastructure needed to handle model maintenance. And the idea of model maintenance is this. So when you do deep learning, you make some trade-offs. And one of those trade-offs, excuse me, is that your model will drift. And your model itself isn't changing, but what's happening is the world changes. So because your model is trained from data, right, as soon as a new data comes along, I guarantee you there's going to be some differences, right? And traditionally, machine vision systems, the focus has been keeping things very consistent, right? Keeping the lighting consistent, keeping the positioning of the part consistent, and that's great. But even there, they can struggle because the world does change. Colors change, things wear out, parts change. And deep learning is no different. So the models do generalize well, but you're probably not going to have the same model in production for 5 years. We don't see that happening with our customers. Now, that raises an important question of how often do I need to retrain my model? And we found that around quarterly is about right for the applications that we're seeing today. So built into our subscription model is a retraining service. And this is a really important part because traditionally, I think folks have thought about machine vision as a kind of set it up once and then hopefully it runs for 10 years. But with deep learning, we think that there's a necessary shift in focus that has to happen where now it's more about making a system that is designed to be changed. It's designed to be maintained. So that really is a challenge. And let me kind of talk you a little bit through how we address it. So here is a dashboard that we would deploy for a customer. And we monitor a number of things. But the one thing that we monitor additionally that maybe is a little bit different is we model something we call anomalies. And these are examples where our current deep learning model is not very confident. So deep learning models will give you a prediction, but they also give you a confidence score. And if that score is too low, we actually flag those and we monitor that rate over time. So if we see a spike in the anomalies, we can actually trigger off that and send an alert. And that generally means that your model, either one of two things has happened. Either you're kind of seeing some natural variation happen over time, or perhaps you're seeing some kind of defect you've never seen before, right? And we have some more technical slides and descriptions that we'd be happy to share via a call, a one-on-one call, about how we actually achieve this. But this is really, really important because, how do you actually know if your model is doing well? It's a big challenge, So I presented you with the accuracy numbers from before, and that's great, but you can't actually measure accuracy in real time. The reason for that is that you need human labels to compare against. So in production, we can't just measure accuracy. So it introduces a whole new set of challenges. Okay, so for model maintenance, we really think that building the infrastructure in a way that allows you to quickly redeploy models is critical, and that's where we lean very heavily on the Microsoft Azure stack to do that. And we think performing regular retraining is critical. We think that is really the path forward and how deep learning is gonna win in manufacturing. The final piece and the final challenge that we spend time on here is really the change management. So hopefully this last topic has maybe got you thinking a little bit about how deploying and kind of the organizational structure that goes around deep learning and how that might need to change in an organization. So as I mentioned earlier, traditionally for applications where high quality is needed, it's very common to use humans for manual inspection. Deep learning is making that less of an appealing option because we can generally do better than humans given the right training set. But there's a new set of needs that arise when you deploy a deep learning system. So for example, we have these dashboards now, and these indicate, these are examples that need to be retrained. And labeling these anomalies and tracking this performance, these are exactly the tasks that need to be done regularly. And we think these kind of tasks are what are replacing the manual inspection task. What's really great with deep learning, as I mentioned earlier, is there's a number of methods you can also use to figure out, what are the examples that really need relabeling. So using, again, the model confidence score that I mentioned earlier, we can have your quality experts only label a small portion of the data, but we can choose the portion that's going to be most informative. So we think this creates a lot of new opportunity. But it is a new frontier here where you have to kind of change how your organization approaches machine vision and quality, where it's going to be this continuous improvement process as opposed to kind of a set it and forget it kind of thing. So we really think that the deep learning is best viewed as a continuous improvement QA/QC tool. All right, so those were kind of the three myths and the three challenges that we see out in the world today. And I'll just finish up by tying back to a few real-world examples. So you can probably tell that I really enjoy talking about the technical side of this. I think it's fascinating, but the business side is really important too. And as Robbie mentioned, without the business impact, and just like David mentioned, 2 out of 3 pilots will fail because they aren't driven by a real business case. So at Mariner, we generally try to get the business case in place first, right? Because if you can't drive business value, it's just it's never going to be put in full production. So here's just a few numbers, and really instead of just emphasizing these results, what I'd like to do is maybe mention the variety of results. So when we first got into deep learning for visual inspection, like I said, about a year and a half ago, we really thought that the main value driver was going to be improving output quality, right? We can reduce missed defects, for example. And that's been true, and we've been able to get some good results, in some cases, up to 10x over existing systems. But at the same time, there's actually a number of other benefits that come into play when you deploy deep learning for visual inspection. I'll just mention one, which is root cause analysis. So traditionally, many vision systems are really just designed to detect good versus bad parts, right? And that's exactly what you need if you're making real-time decisions. But with deep learning, we can pretty easily go a step further. So that Fabric company that I mentioned at the beginning, they started with around 7 different classes of defects. So you saw stains. They have a bunch more, and now they're up to around 20. And they actually have tied this whole deep learning system with our help and with some work from their IT department into their ERP system. So what that means is that as soon as we see a certain type of defect, right? So we might see a series of stains in a row or a series of what's called a pick in a row. If we see that, we automatically trigger an alert. And we know, using some business rules basically, that this roll came from this certain machine in the factory, and they can go fix that machine way more quickly. So that process, just to give you a rough feel, that would have taken on the order of weeks to maybe a month to actually do that traceability in the past. And now they can get that alert in literally minutes, right? In just a few minutes. So having that root cause analysis by having this really granular breakdown of the kinds of defects that we see gives tremendous more insight and business value than just having good bad, right? So good bad is a great starting point, but being able to break apart the categories of defects we found is really, really, really powerful. Okay, great. So I'll just end with one little bit about how we get started normally. So just like Robbie said, we typically start by defining success. What are you looking for your business? What makes sense? And on the visual inspection side, we normally then ask for a set of images, and we do an initial modeling analysis to see if we can achieve the performance we need. That really helps us de-risk these problems at the beginning, and that's how we typically start these engagements. So finally, if you'd like some more information, please visit our website. And then also, we love hearing about applications of deep learning. And every call is really, manufacturers are very unique, and I love hearing about different applications. And if you have any questions, please reach out as well. So you can email me directly at steven.welch@mariner-usa.com. And I look forward to hearing your questions. And I think I'll stay on this slide. I think I'll hand it back over to Rob. Yep, that's right. And we'll take any questions that you have. So thank you so much for your time today. And hopefully it was worthwhile.
Great, thanks, Stephen. We do have a couple questions from the audience. First question was, will the slides and recording be available after the webinar? Absolutely, they will. We'll provide those to all attendees. The next question is Mariner's SVI product compatible with all vision systems?
Mostly, yeah, it's a really good question. So we try to be as open as possible. We are not in the imaging space, so we would like to be as compatible with as many as possible. There's a few systems out there, and we're happy to, on a call later, detail how we see the whole landscape. But there are a few systems out there that are more closed and proprietary, where we really can't get at images, and those we unfortunately are not compatible with. But we strive to be as compatible as possible. And as I said, if you'd like to hop on a call, we can talk about specific systems versus others.
All right, another question. Can you comment on the application of deep learning to streaming video versus still images?
Yeah, good question. So as far as I'm aware, and I try to stay fairly on top of the literature, there hasn't been really any big breakthroughs in video that I've seen. That doesn't mean we can't do well on video. All it means is that to analyze a video, we just break it into stills. We analyze those separately, and then there may be like a tracker that we apply on the end to like temporally smooth things out or something. So certainly deep learning can deliver dramatically better performance on video than other traditional computer vision approaches for many problems. However, there's no like magic video deep learning. It really is just doing image analysis on a series of stills, really is kind of where the state of the art is today.
All right, another question. We touched on some of this before. Do you need to have a machine vision system installed to benefit from Spyglass visual inspection?
Yeah, so you definitely don't. As I said, we have a really great system integrator partner. They're one of the biggest in the country for vision integrations, and they're great to bring in. They bring a lot of knowledge and expertise on the actual physical, putting in the cameras, which can be really tough, especially if you have a reflective product or a small product, or there's all those different variations that can happen where a simple, inexpensive setup just won't cut it. So they're really, really good at configuring the right hardware you need to get good quality imagery.
All right, another question. This may be more towards Robbie. What is the average subscription price for SCF?
Yeah, Rob, obviously it's going to vary per application, but just to kind of get started and think about it, it's software as a service. So a yearly fee, probably up to 20 machines, around $35,000. The implementation, I'd say probably total under 50,000 for initial implementation. And then as you exceed machines, I think up to 200 machines, you would be in the $65,000 to $75,000 range total. But it's very application dependent. I'm happy to talk more specifics with anyone interested in getting a little more detail there.
All right, next question. Do you have the application stack diagram you can show with indicators that show how the application tied into the customer system?
We do have one more detailed slide. Let me see if I can get to it quickly here. Here we go. This is more from the Microsoft perspective. This really shows the different Microsoft components that we're using. This has a little bit more to share about how we tied into the existing system, but this is kind of the general case, and then depending on certain customers, these protocols might vary. So yeah, if you'd like to hop on a call, we'd be happy to walk you through specific integrations via, a lot of times we'll just use network shares. So this connection will be over a Samba network share or a just general TCP/IP network share, so we can access data in real time. But this is the most specific slide we have for you now, then we'd be happy to answer in more detail on a call. Good question.
All right, and last but not least, I think we touched on this, or Robbie may have earlier. What happens if your solution doesn't work?
You can get your money back. We're confident in the technology, Rob. We've proved it out. We know it works. The focus is now on the business application and being able to provide the right business value to the right people at the right time.
Right.
All right. Thank you, guys. Okay, I think that is all the questions. Again, thank you all for attending today. We really appreciate you taking the time, and everybody stay safe, and hope to see you on another webinar. Take care.
Thanks, everyone.
Thank you.